Okay, so in this video we're going to look at relations and some properties of relations. And so first things first, I guess, would be let's talk about what a relation is. So a relation is going to be, if you've already talked about the idea of a function is a specific type of relation. And so when you talk about a specific relation, I've written one here on the screen, right? We're just using this notation to mean, this basically means x is related to y. Sometimes you see this written x or y, x related to y. But the ordered pair notation is very common as well. And so x is related to y, and you need some condition to define how those are related. So in this case, the example that I'm using is that those two are related if x divides y. If x divides y. Now, I'm using the more formal mathematical definition of divides. Of course, any two numbers can be divided, right? But in a more formal sense, we would say that 3 divides 6. Because if I take 3 and divide it into 6, there's no remainder, right? I get 2 if I do that. So I wouldn't be able to say, for instance, that 4 divides 6. In this sense, we're using a more formal definition of divides. 4 does not divide 6, because if I try to divide 4 into 6, that doesn't come out to be an integer, right? I get some decimal or fraction when I do that. So when we use this word divides, that's what we mean. In this case, in plain English, it would be divides evenly, I guess might be a better way to have said it. And I've defined the set x, 2, 3, and 4, and the set y to be 3, 4, 5, 6, 7. And so this is an example of what's called a binary relation because the first element in our relation has to come from this set capital X, and the second element in the relation has to come from this set capital Y. So the way that I'm going to write out the elements of my relation is it's going to be a set of ordered pairs where the first the x value comes from these numbers and the y value comes from these numbers. So what I'm kind of doing one by one, let's start with the elements of the set x, and then if I go to my set y, I'm looking for any numbers in y that can be divided by 2. Okay, so 4 can be divided by 2, 6 can be divided by 2. That means that in my relation, 2 is related to 4, and 2 is related to 6. In other words, 2 divides 4 and 2 divides 6. Right, and then we can go and look at our next element of the set x. And in my set y, I want to look for numbers that 3 divides. Of course, 3 can divide itself. 3 divides 3, and 3 can divide 6. And then lastly, we can look at the number 4, and what elements from the set y does 4 divide? 4 can divide itself, and it looks like that's going to be it. Can't divide 5, 6. If 8 was over here, 4 could divide 8, but that's not in our set y, so we have just 4 related to itself. Okay, and so sometimes all we want to do is just list the elements of a specified relation. Again, this is called a binary relation because we have one of our coordinate points came from this first set x, and the other point y came from the second set. It involves 2 sets. A lot of times, however, what we have is a relation that's just defined on a single set. So let me kind of explain that as I go on to the next topic, which is the idea of a reflexive relation. So here's a little bit more formal way to define what it means to be reflexive. So for all elements in our set, x has to be related to x, or x comma x is in the relation. And so notice here I'm not defining a binary relation in this example that I'm going to show you. We have this relation. So in this instance, I'm not going to list out the elements of the relation. They're already here for us. This is some relation, right? This relation R is defined on the set X. Right, so what that means is that, for instance, in my first example, right, we had one set X, which is where our little x's had to come from, and a separate, different set Y, which is where the little y's had to come from. So if you see the relation defined just on a single set, what that means is your first set is 1, 2, 3. And rather than listing a second set Y, we just define the relation on the set X because Y is going to be the same set, right? So my little x's have to come from this set X, and the little y's come from the exact same set, 1, 2, 3, right? So it's easier just to define a relation on a single set. And that's what we see in this case. So the question that we want to think about in this example is this relation reflexive? And so when we're already given the elements of the relation, we can simply do this by inspection. And so what we're looking for is, are all of the elements in our set X, which is here, right? Do we have every element in this set X related to itself, right? That's what this piece of the definition of reflexive means. So we have to have 1 related to 1, 2 related to 2, and 3 related to 3. So here we've got 1 related to 1, 2 related to 2, and 3 related to 3. So in this case, yes, that relation is reflexive. And so you can see it would be pretty easy to create some relation on X that is not reflexive. All we'd have to do is kick out one of these. Right? If we knock this ordered pair out of the relation, then we'd have 1 related to 1, 3 related to 3, but we'd be missing 2 related to 2, right? This has to be true for all elements in our set X. Okay, so that's what it means for a relation to be reflexive or maybe not reflexive. All elements related to themselves. And so let's look at another idea, which is called symmetric. Right, so now you see here, and again, this relation is going to be defined on the same set. In fact, I think it's the same relation. It is the same relation. And so now in my definition, you see that we have a condition that's true for all little x and little y in our set X here. So again, we understand that the set Y is the same set. Okay, so both little x and little y come out of this same set. So for symmetric, we have that if this is true, if x is related to y, then this is true, y is related to x. So if x is related to y, then y is related to x. And so again, when you're given the elements of the relation, you can kind of just go through and do this by inspection. Of course, if you look at some element like, say, 3, 3, well, okay, if we have 3, 3 in the relation and we flip those around, right, so we switch these, it's going to be the same element, 3, 3. So, of course, this if-then statement is going to be true. If 3, 3 is in our relation, which it is, then we flip those elements around, then 3, 3 is also in the relation. Right? So same thing's going to be true for this element and this element. So those fit the definition of symmetric. But what about these two over here? If we have 2, 1 in the relation, which we do, then what we have to check for is, do we also have 1, 2, if I reverse those elements, right? So if I flip these guys around, do I also have 1, 2 in the relation? And I do, because both of these are there. So